Today we're going to take a look at Cyc. In the interest of full disclosure, I personally worked at Cycorp until 2005. I've tried to incorporate more recent information, but I apologize if any of my knowledge is a little out of date. So today I'm going to explain what Cyc is, explore some of its history, and look into some technical details. Before I get into any details, let's start by discussing at a high level what Cyc is for. It's supposed to be genuine common sense AI. Here are three different ways to express that concept. We want computers to be able to do some of the sort of real-world reasoning that humans are capable of. In order to achieve this, the computer needs to have the background knowledge that humans bring to any task. For example, an encyclopedia will explain complex subjects in terms of simpler ones, and it's assumed that the reader will know basic facts about the world like you hold your coffee mug with the open end up and horses have heads. The writer of the encyclopedia assumes that the reader knows these facts and never states them explicitly. These facts are referred to as the white space of the encyclopedia. Finally, they want computers to work like they do in movies. A commonly used example is the HAL 9000 computer that appears in the movie 2001: A Space Odyssey. Next time you watch that movie, think about how much HAL has to know in order to be able to show the flexibility it does in interacting with the humans. As Doug Lenat, the founder of Cyc, puts it, intelligence is 10 million rules. If we can teach computers the rules, then it will be able to behave as if it's intelligent. Let's start with some key terms. So the Cyc Project was an effort to produce genuine common sense AI. It was started at the Microelectronics and Computer Technology Corporation in 1984. Originally conceived as a 10-year project, it's now in its fourth decade. The idea was to use symbolic reasoning to allow computers to do human-like reasoning with the ambition of making computers less brittle. The Cyc Project was started by Doug Lenat, an accomplished artificial intelligence scientist specializing in symbolic reasoning. His previous projects include The Automated Mathematician and Eurisco. In 1985, the Cyc Project was spun off into a new company called Cycorp. Cycorp is based in Austin, Texas, and Doug Lenat has been CEO for its entire history. Cycorp employs many ontologists, computational linguists, and programmers. Cyc is the software produced by Cycorp and the Cyc Project. It comprises a knowledge base, an inference engine, and various interfaces. The knowledge base is canonically represented in a special declarative language called CycL. We'll see some examples of that later. The inference engine is implemented in another in-house language called CycL, which is a dialect of Lisp. Cyc also has a variety of interfaces, including a web-based concept browser. The Cyc software has been released in many versions over the years. There are three main versions you're likely to hear talked about. OpenCyc was an attempt to produce a limited open-source version of both the knowledge base and the inference engine. It was first released in 2002 and, as of 2018, it is no longer supported. ResearchCyc is a fuller version of Cyc that's licensed to certain research institutions. Finally, people talk about full Cyc to describe the version available internally in Cycorp. The CycL language is sometimes described as being first-order predicate calculus with some higher-order extensions. If that doesn't mean much to you, don't worry about it. Syntactically, it looks very much like Lisp, as it uses the same surface syntax, which is known technically as S-expressions. This means that you'll see lots of parentheses. You might want to compare CycL to other representation languages like RDF. The major difference is that RDF is limited to triples, but CycL can handle unary, binary, and higher or variable arity relations. CycL is also not limited just to simple properties, but can represent predicates, functions, logical connectives, and quantifiers. This allows it to be used to represent simple ground facts, rules, queries, and denotational terms, all in the same language. RDF can represent all of this, but the language does not support it well, so it quickly becomes clumsy. Further, CycL supports meta-assertions where you can represent facts about an assertion. Again, you can do this in RDF using statement reification, but it's painful and inconsistent. Another thing that Cyc supports is non-monotonic reasoning. Any assertion can be monotonically true, or always true, Or it can be merely default true, which means that exceptions might exist. For example, all birds can fly is only default true because of penguins. Assertions can also be monotonically false or default false. I should point out that it is possible to project the entire Cyc knowledge base into an RDF-AL representation, but you lose a lot of elegance of expression when you do it. So the Cyc knowledge base represents millions of concepts and tens of millions of assertions relating them. Concepts range from the universal thing at the top through an upper ontology containing philosophical concepts like individual, collection, event, social organization, intangible object, and so on. The middle ontology contains more specific concepts like humans, cats, and dogs. Finally, there's a host of domains that have been fleshed out with knowledge targeted at some specific application, like chemistry, terrorism, or military planning. The assertions are organized into groups called microtheories. Microtheories differ from each other by the contexts in which the assertions are considered to be true. For example, a microtheory might represent a specific source of information, or the time or place in which a fact is true, or the language for some lexical term, or even the group of people who believe some claim to be true. Every assertion is made in a specific microtheory representing its context. At query time, microtheories inherit from each other to build a consolidated inference context. Hence, a query might only consider facts that are true at some time, or in some language, or some part of the world. This might seem like a lot of hard work, but the conceit of the Cyc project is that there are no shortcuts to common sense AI. As Doug puts it, sometimes the veneer of intelligence is not enough. Here are some examples of simple assertions in CycL that you might find in the Cyc knowledge base. For example, the collection dog represents all dogs in the world, is an instance of biological species. As a collection, it's a subcollection of carnivores. Bill Clinton is a specific individual and he's currently married. Cycorp has a general rule of thumb that it isn't worth reifying or representing a concept unless you can make at least 10 assertions about it. These three expressions are called ground atomic facts because they contain no variables and no logical connectives. The final example here is not a ground fact because it contains two variables. Some car has some color. Notice that in CycL, the predicate always appears first. If you're accustomed to RDF, you'll find yourself thinking that the property appears between the subject and the object. But for variable arity expressions, it's helpful for the property to come first. Here's an example of a rule in CycL. So the important thing to know about rules is they relate some antecedent condition to some consequent conclusion. In this case, the antecedent is a conjunction of three separate conditions joined by and. First, we must be dealing with some instance of the giraffe collection. Second, we must have some instance of a neck. And finally, the neck must be part of the giraffe. So we have some giraffe's neck. The consequent is that the neck in question has a spotted pattern. Here's another example rule. Here we say that if we have some instance of dog, then there must exist some instance of nose that's a nose that the dog has. So earlier I mentioned that in addition to properties, CycL has logical connectives and quantifiers. We've seen the logical connectives implies and as you might expect, there are also or and not. In addition, Cyc has quantifiers like there exists and for all, which provide a binding context for some variables. The Cyc knowledge base is full of knowledge like this, but there's a much more elegant way to write it, known as rule macro predicates. The ternary relation all exists is merely a shorthand for the rule above, and it allows you to write it as a simple ground fact with no variables in sight. The definition of the predicate tells Cyc what the rule expansion is, and it allows the inference engine to use these assertions in reasoning. So to the inference engine, the simple ground fact at the bottom can be used just as readily as the rule stated at the top, but it's much more obvious for an accustomed CycL author to write. So there's a lot going on in Cyc, and I don't have time to go into all of it, but I want to drill down into one aspect in particular, and that's natural language processing. Now, the history of NLP and Cyc is rather interesting. A lot of people who encounter Cyc for the first time assume that NLP must be the driving application for this technology. In fact, for the first decade of the Cyc project, there was little emphasis on NLP at all. Instead, it was assumed that humans would meet Cyc halfway, representing knowledge in queries in CycL. This changed around the turn of the century, and several different projects were started within Cycorp to allow Cyc to read and write in natural languages. So this is not as crazy as it sounds because there are many language-independent aspects of understanding language, like discourse management and for resolution, that Cyc can help with without having to deal with the rest of language understanding. So there's a general rule in Cycorp that you're not allowed to create knowledge representations that are not in CycL and are not stored in the knowledge base. This is also true for the Cyc lexicon, which is stored as assertions in appropriate microtheories. This lexicon is used for two distinct purposes: generation and understanding. Generation is the production of natural language from CycL representations. It can be used to explain the knowledge of it can be used to explain the contents of the knowledge base, to answer questions, and to explain the reasoning behind an inference. It can also allow Cyc to ask the user questions, perhaps as part of interactive dialogue. Natural language generation is very well developed in the sense that almost any CycL expression can be presented in English. Interestingly, some of the main problems with generation relate to knowing what parts of an explanation are too obvious to be worth stating, or too abstruse to attempt to explain. These are known internally as the does and has. The harder problem is to allow Cyc to read natural language text and convert it into CycL that perfectly represents it. When I left Cycorp, this was working well for form-based UIs and understanding the answer to specific questions and interpreting the results of highly targeted fact extraction. Cyc has a two-stage representation of its lexicon. Individual words, or roots, are reified in lexicon microtheories. These are CycL terms that are associated with their various string representations according to inflection rules. These word terms are in turn linked to language-independent concepts. This means that concepts are never linked directly to strings. An exception to this is named entities, which are concepts that have direct name properties, and also rules for deducing additional names. Here's an example of a named entity that we know three facts about: a first name, a last name, and the knowledge that she has a PhD. Here's a rule that says if you know those three facts about a person, you can build a new name string for the person by connecting them together. And here is the consequence of that rule worked out for these ground facts at the top left. Here's an example of a template that's used to generate natural language text from CycL. This template explains how to generate the predicate that's called extent cardinality. For example, if you have the assertion extent cardinality famous 5, 5, that tells you that the group famous 5 has 5 members. And this template lets you generate the text, the famous 5 has 5 known members, and for linguists that corresponds roughly to the linguistic parse template shown on the left there. Here are some rules that describe how to perform inflectional and derivational morphology. Gerunds are pluralized by adding an S. The universal past tense of a verb is formed by adding ed to the infinitive. The agent noun from a verb may be formed by adding er to the infinitive. You can get the comparative form of an adjective by adding er to the positive, and so on. Notice that these rules are all specific to English, and they are merely defaults because each one has exceptions. Remember that the lexicon is two-stage. Words are represented separately from their denotations. Here are 4 different assertions that attach a meaning to the word ring. It's a verb meaning to emit a sound. It's any ring-shaped object, it's an audible sound, and it's a type of jewelry. Here are 6 denotations of the word Coke. It can be a serving of Coca-Cola or a generic cola drink, or a mass noun for the substance. It can refer to a drug or a type of coal. Recall that one thing CycL has that RDF does not is the denotational function, and here we see an example, serving fun. This function takes a single argument which is some substance, in this case Coca-Cola, and it denotes a single serving of that substance, like a glassful or a canful. There's a newer form of templates used in Cyc called semantic construction grammar. So consider the expression big blue building. And suppose we have two templates for relating text to CycL. One of them says that some color followed by some type of partially tangible object can be represented with the CycL there shown in blue, which says that it's the subcollection of the partially tangible objects whose main color is that color. And the second rule says that the literal word big in English, followed by something which has positive dimensions, can be represented as a large thing with positive dimensions. Notice in these templates that there are terms starting with a $sign. Now they look like ordinary Cyc collections, like dollar color. Like color is the collection of colors, but they are in fact a sort of placeholder for some subcollection of that concept. For example, building is a subcollection of partially tangible objects and also positive dimensional things. Blue is a child of color. So given these two templates and this natural language expression, we can use recursion in the linguistic sense to deduce that big blue building has the representation shown at the bottom. It's a large version of the subcollection of buildings whose main color is blue. So far I've been talking mainly about CycL and the Cyc knowledge base, what sort of things can be represented in it. I should spend a little time on some other aspects. Cyc includes a general purpose reasoning engine. This means that conclusions can be drawn from any arbitrary combination of facts and rules. Technically, CycL is powerful enough to represent systems that are undecidable, and the complexity means that answers are usually best effort rather than complete, as would be expected in, say, an RDF Sparkle query. Fortunately, the general purpose reasoning is supplemented by a suite of special purpose optimizations. These are automatically engaged by the reasoner, and in general answer questions that could have been answered by general purpose reasoning, but just not as fast, and hence possibly not in any reasonable timescale. One example of a special purpose optimization is subsumption reasoning. This is where you know that one concept is an instance or subcollection of another, or some predicate is transitive and therefore has a transitive closure, or a predicate has subpredicates, so if someone has asserted a fact about a subpredicate, you can deduce the same fact about the predicate. These are the most common types of reasoning performed, and they are therefore very highly optimized. When we talk about rules, we usually think about matching their consequent in the query. So we take a query, we see if anything in the query looks like the consequent of a rule, and then we work backwards from the query to ground facts. Technically, those are known as backwards rules. Selected rules can be marked forward, which means that when we assert the rule, we match its antecedent to known facts and automatically add any consequences to the knowledge base as automatic forward assertions. The same thing happens when we add a new fact. We check all the forward rules that we already know about to see if they have any new consequences. This automatic process of keeping the knowledge base consistent as it's being changed is called truth maintenance. Finally, every answer produced by Cyc inference is associated with an explanation of why Cyc believes the answer to be true, citing all the supporting rules and the ground facts. Explainability is important to humans who may not trust a computer absolutely and may want to dig into what the sources of the information are. there's one more aspect of the Cyc knowledge base that I want to cover. Cyc does know about many named entities and facts about them, like Bill Clinton as we saw earlier. But the important things in the Cyc knowledge base are the collections and the rules. And Cycorp doesn't want to pour in every fact about every individual into the knowledge base. Instead, Cycorp has developed technology that allows them to integrate external knowledge sources into Cyc's inference. CycL is used to represent how to connect to some knowledge source, such as a SQL database. For every table in that database, each row represents an entity of some type, such as a person, and then the columns of that table represent facts about that person, like name, occupation, social security number. Now, when we run a query in Cyc, the inference engine automatically federates it to the external knowledge sources. The person posing the query does not have to worry about where the information is stored. Native knowledge is seamlessly integrated with the external knowledge. So, I've been talking so far about interacting with Cyc using CycL. I wanted to give a quick teaser of some of the interfaces Cyc has for interacting with people. Here's one that gives forms that can be used either for knowledge entry or for browsing fact sheets about known entities. In knowledge entry, the natural language understanding task is greatly simplified in a form because of the narrow range of plausible answers. It's going to be a simple noun phrase of a known type. For browsing, you can drill down into why Cyc believes each fact, showing the source of the information so that an analyst can assess its reliability. Here, we see an example of interactive clarification dialogue. Cyc has come up with 4 plausible interpretations for the user's query and is asking which one the user meant. Here is a tool that allows an analyst to build a CycL query without ever having to see CycL. The analyst merely has to select and combine query fragments that are all expressed in English. And finally, here's an example of a proof tree or a fragment of a proof tree provided by Cyc as the explanation for some query answer. All of these examples come from Cycorp publications, and if you want to know more, they're all linked to in the respective documents if you look at the slide version of this talk. So I've already spoken about some of the possible applications for Cyc, such as supporting data analysis, discourse modeling, and anaphora resolution. I want to highlight a couple more that are interesting. Here's an example application for Cyc. Suppose that someone wants to find a picture of someone smiling. Now, suppose that we have a database of images with captions, and one of those images is captioned, "A man helping his daughter to take her first step." Now, Cyc would know that parents love their children, that taking your first step is a great achievement, that helping people you love achieve things makes you happy, and that happy people smile. That's a lot of background information to link those two things. Here's another application that's currently in beta, and you can find it on the Cycorp website. This allows Cyc to help children to learn mathematics. It does it by role-playing another child that is slightly behind the user in their mathematical understanding. Students have to teach the in-game protagonist to solve mathematics problems, finding and correcting their mistakes. So I want to close with a quotation from Doug Lennett's recent TEDx talk. He's talking about what the world will be like once we have superintelligent computers. We will look back on pre-linguistic cavemen and think, they weren't quite human, were they? In much the same way, our descendants will look back on pre-AI Homo sapiens with exactly that mixture of otherness and pity. Thank you for listening.